All right, folks. Well, I wanted to come back and talk a little bit more about sort of parsing Lisp in Lisp. So the idea is, suppose we want to be able to look at the code for a function and actually decompose it, figure out, where the parameter list is supposed to be, maybe build a new function that takes the existing function and adds extra parameters and adds extra functionality, or just tries to pull apart different pieces of the function. Again, we have to be able to do things like say, well, is it a compiled function or is it a regular function? Figure out what form it has, extract the right pieces from the right places. And there are a few complications as we work our way along the line that'll let us introduce some appropriate use of macros. And then we'll go from there into talking about just sort of general parsing Lisp in Lisp. So that's kind of where I want to go for this session. Again, we mentioned some time back that functions could be compiled. Functions can be an actual lambda expression, or it can be a function built by a call to a lambda, or by a call to defun, or by a call to labels, or use in a labels block. So lots of different ways that functions can be created. Some of the built-in constructs that we see in Lisp are actually provided through macros, so those are going to work a little differently than functions. So if I'm just taking something and taking some Lisp apparent function call or some Lisp statement and trying to analyze it using Lisp, then I've got to be aware of all of these different possibilities. So function p f comes back with true if and only if f is a function. So it doesn't handle things like the macros and whatnot. F bound p is going to be true if f was created using a defun. That shouldn't be a defr, that should be a defun. And function f, or you can use the equivalent, the hash quote f, returns the implementation of a function if that's what we're working with. So we can go through and test to see if something is a compiled function. So this is perhaps one of the ways we would start off. See, is it a function? If it is it a compiled function? So if so, it will return the symbol compiled function. So we can test that and say, oh, well, I can't really analyze the format of this because it's compiled. Otherwise, we'll wind up seeing one of a bunch of different things. Either the structure if it was created with a defun, or maybe somebody actually passed us a lambda call, or if they passed us the result of the lambda call, so the actual constructed function, so that'll have the lambda closure, the environment lists, the parameter lists and whatnot, whereas the defuns will have the lambda block symbol, the name of the function, the parameter list, etc. Or if it was created in a labels block, then it'll come back with the lambda block closure symbol, the 3 environment lists, and then the name, parameter list, and body. So different formats, but we can identify which one it is by taking a look at the symbol in front and saying, okay, that will tell us uniquely which one of these kinds it was. Now, bit of a complication. That function is actually an operator, not a function. So this thing that we're trying to run on f to figure out what the structure of f is, this function is actually an operator, not a function. So that introduces some complications when we're trying to use it, because it also only works if f is actually the name of the function. So we can't call function x where x is a variable that holds the name of the function. So that gets a little more awkward, because now we've got this operator working on something that has to be the actual literal name of the function. And furthermore, the function that we're trying to access actually has to be in scope right now. So let's suppose I had something like get params, and I wanted to write this function to get the parameter list of any function that was passed to it. Now, because in my getParams function, the name foo would be stored as one of the parameters, I couldn't call function on that parameter and have it work because function expects to be given the actual name of the thing. It would need the function foo. So again, we start running into issues here in terms of how we can have getParams run this function. So I could make the user actually pass function foo to getParams, but let's face it, that's kind of clunky for the user. It really seems to make more sense for the programmer to be able to say getParams foo and have things work it out. So what we could do instead is to have getParams as a macro, where it will rewrite getParams foo into something that actually extracts the parameter list. So here, we could have extract params foo rewritten as extract params function foo. So here we're actually getting our macro to do the work for us. So it means going back and writing a macro for this, but it's one of those places where the nature of what we're trying to do isn't suitable for function calls, so that makes it a good candidate for rewriting as a macro. All right. The user could still make their, getParams foo call, and we transform it. And we take getParams, again, rewrite into our extract params, which goes off and does whatever it's going to do. And then we create, we're having our macro rewrite We're having our macro rewrite getParams into extract params, where extract params is our actual function, but we're passing it the result of our call function f. So the developer does this, our macro rewrites it to this, and then our function is actually being passed the implementation of f. I'll get it right. So we can go through, make sure that f was actually a function, just in case somebody calls extract params with some other garbage rather than through this method. And then we'll go through and we're going to try and build up which type of function it is and analyze it appropriately. So we'll make sure that this thing is actually a list, right? If they're passing us an implementation, then it should actually be a list. And so in that case, we'll go through and look up whatever the front list element is. I should probably check and make sure it's not null as well. But we'll take that front list element. I guess if the thing is a function, it must have some content to it. So we'll take that front element, extract whatever that symbol name is as a string and store it. And we'll check and see if the type of our function matches something that we're expecting. So if the type of f is a compiled function, then we'll say, it's a compiled function. Otherwise, we'll go through and try and figure out what the actual parameter list is. So if it's a compiled function, we can't extract the parameter list. Otherwise, we can go through and that string that we stored in f-type is going to be one of the different lambda whatevers. So it could be either our lambda block, or pardon me, our lambda, in which case it's an actual lambda call, or lambda block closure, or lambda closure, or it was our compiled that we just figured out a moment ago. So based on whichever type we got, we'll look up the right position in f to get the parameter list. So if it's a lambda, it's the second thing in. If it's a lambda block, it's the third thing in. If it's a lambda closure, it's the fifth thing in. If it's a lambda block closure, it's the sixth thing in. And if it's compiled, we can't do anything about it. We'll just return compiled. So we can go through and extract the parameter list based on our knowledge of what kind of function this must be. And if it's anything else, we'll just throw an error. Right, so we can go through and start thinking about just exactly how's an effective way from the developer's point of view for us to provide them with access to contents of the structure that we figure out at runtime. Now, again, this still doesn't deal with the built-ins, things like, if somebody passes a cond to this or somebody passes a let to this. So maybe what we start doing is saying, well, If it's one of those things, then we'll just create a lookup for where to find the parameter list. Right? So we could create a hash table of all of the different Lisp built-ins that we know of, and for each of them, figure out, okay, well, where do we find the part that we're interested in, and what are we interested in? How do we extract that? Right. So if we're looking at something like a defun, then we know that the structure is going to be a function name, a parameter list, and then a bunch of other stuff. So we can go through and extract that parameter list. If it's a let block, we know that the structure is going to be that list of pairs and then a bunch of other statements. So we can think about what the structure of these things are and then return the appropriate values. Now, if we want to get a little fancier, instead of just returning the actual parameter list, maybe we go through and say, well, this is a function that, and what we'll try and do is figure out how many parameters that function expects. So maybe what we'll do is say, well, it would be easy if they were all mandatory parameters, but they might not be, right? We might have some mandatory parameters, some optional parameters, and it might be variadic, so there might be any number of additional parameters. So now let's say we want to tweak our little analysis function here to go through and say, well, let's write it as a lookup arity, where we'll go through and figure out how many required parameters there are, how many optional parameters there are, and whether or not you're allowed additional parameters. So what we want the programmer to be able to do is to use this lookup arity and the name of their function. And of course, we're going to rewrite that into a call to extract arity, which is going to be our function that does the actual work, and pass it the implementation, the structure of our function. So we'll pass the results of function f. So similar sort of idea. And we need this extract arity function that's going to go through and figure out, well, I guess we're going to look at extract params, right, the one that we wrote previously, to get the parameter list from f. And once we've got that, we'll go through and try and figure out how many of them were required, how many of them were optional, and whether or not additionals were available. So any of these could be present or missing, right? There might be no mandatory parameters, there might be some, there might be no optional parameters, there might be some, there may or may not be an and rest. So we'll have this return maybe 3 values. The first one will be the number of mandatories, the second one will be the number of optionals, and the third will either be a true or a false to say, yeah, does it support and rest? And again, we can use multiple value bind and the values option to pass these back and forth. So if our parameter list can look something like this, then really what we want to do is figure out whether there's an and rest in there, and whether there's an and optional in there, and how many things there are in between. So if we kind of carve this up into 3 separate lists, the mandatory stuff, the stuff in the middle, and whether or not there's anything on the end, then that will go through and let us figure out how many of each type there are. So we want to get a list of everything that's before and rest, a list of how many things are in just the optional after we've got rid of the and rest, and then a list of what we've got after we get rid of the and optional, and then just count the sizes of the 3 lists. So you can use position and some element and a list to figure out where something is, and subsequence of your sequence and a couple of positions to extract positions and subsets of a list. All right, so we could go through and say, let's keep track of our mandatory parameters, our optional parameters, and the rest, and we'll assume that it's nil, and we'll throw everything in the mandatory and everything in the optional. And then we'll go through and say, well, if there's an and rest in there, then I'm going to say, yep, you are allowed this is a variadic function. And what we'll do is revise that optional parameter list, and we'll just take everything before the and rest. So now our optional list has chopped out the and rest and whatever was after that. and we just keep plowing ahead. If and optional is in there, then we'll do a similar sort of thing where we'll say, well, let's count how many things were after and optional. So we'll get this subsequence of stuff that goes from just after the and optional to, or well, from the and optional to the end of the optional list, subtract 1 for the and optional keyword. And then we've got how many things there are in the optional parameter list. And then for the mandatory one, we'll just keep everything before that and optional. Right? And just the number of mandatory parameters are just whatever that length of that last element is. So we can go through and figure out, we can do a fairly careful analysis in spite of the kind of various different options Lisp provides us with for how something might be structured. And this is kind of the idea of going through and parsing Lisp in Lisp. If we've got Lisp code that's going to analyze Lisp code, it's just a matter of sitting down and figuring out what the possible structures are, how I can figure out which structure is actually in use, and then how to extract the pieces that I'm interested in, how to identify their values and their meaning. So it's quite often going to be something like this, where we go through and create a set of macros to get things in the right format and to allow us to use the operators that we want to use, and then optional or macros or functions to go through and extract the pieces that we're interested in, and just keep building and building and building on the functionality that we've got so far. And if you think about things like read and eval in Lisp, they've already got the ability to do all this. So all of this has been done at some point. It's complex, but it's certainly possible, and you can take a very incremental approach to building up any kind of code analyzer you want to create. All right, I will leave that there for the time being.